Picking up where we left off last time, I remind you that hemoglobin binds oxygen cooperatively, and this is reflected in what you see over here, which is a sigmoidal binding curve right here. Now, hemoglobin has the job of binding oxygen efficiently in the lungs at a relatively high partial pressure of oxygen and releasing it in the tissues at a relatively low partial pressure of oxygen. You can see that, courtesy of this sigmoidal curve, that oxygen has a much higher affinity for O2 binding in the lungs than it does in the tissue. The affinity is changing. Why is this? Well, one thing we know is that oxygen binding to an individual subunit of hemoglobin alters the affinity of other subunits of hemoglobin for binding oxygen. And this is how this cooperativity is transmitted. I've said it before, but I'll say it again. This is reflected in this S-shaped, somewhat S-shaped binding curve, whereas hemoglobin would look something much more hyperbolic, right? I mean, myoglobin rather. Myoglobin would look much more hyperbolic because it doesn't have cooperativity. It only has one subunit. It actually physically cannot engage in cooperativity and changing response to various oxygen concentrations. Allosteric proteins are things like hemoglobin. Derived from the Greek, we have allos, other, stereos, shape, meaning shape-shifting or other shapes, conformational changes. Hemoglobin, again, an allosteric protein such as hemoglobin means that the binding of ligand to one site affects the binding properties of another site on the same protein. Modulators are ligands. So we have a new term here, modulator, a ligand that can be homotropic or heterotropic. O2 is an example of a homotropic modulator because the normal ligand and the thing provoking the conformational change are one and the same, whereas a heterotropic modulator means the modulator is a molecule that is actually different from the normal ligand. We're going to see an example of that a bit later on in the form of BPG. Stay tuned. Now we're going to turn our attention to the Hill equation, which is a good mathematical treatment and graphical treatment to describe cooperative ligand binding and the nature of cooperativity. If we have multiple binding sites, our equation becomes P plus NL yields PLN. This is because there are N number of binding sites. In the case of hemoglobin, of course, N is 4 because there are 4 binding sites. If we take this equation and we put it into a Ka expression, notice we have to raise the ligand concentration to the power of N due to the stoichiometry of the equation. Then, if we return to our fractional binding equation, theta, for this equation, we also have to raise our ligand concentration to the power of N because we derived this theta from the equation above, this theta equation from the Ka expression. Okay, finally, if we do math, including taking the log of both sides, we end up with the Hill equation itself. The Hill equation says the log of theta over 1 minus theta equals N log times ligand concentration minus log Kd. You might notice this is in the form y equals mx plus b, with m representing the slope or the number of ligand binding sites. The reason this produces a linear graph, of course, is just noted. It's y equals mx plus b, with our y-axis being theta over 1 minus theta, whereas the x-axis is the log of the ligand concentration. Now, the Hill coefficient is actually referred to as NH. and it is, as noted, the slope of our hill plot. If NH equals 1, ligand binding is not cooperative. Basically the binding of a ligand has no effect on cooperativity. If NH is greater than 1, we've seen that with hemoglobin, we have positive cooperativity. And if NH is less than 1, we actually have negative cooperativity. That means that the binding of a ligand actually reduces the affinity of other sites for binding the ligand. This is rare, but not unheard of. Now I want to comment actually on N and NH. So the Hill coefficient in reality, i.e. NH, is always less than the actual number of binding sites. So technically N equals 4 for hemoglobin given the 4 binding sites, but NH is always somewhat less than 4. In other words, let's say it's 3.2. The reason for this is there is no such thing as perfect cooperativity. Actually, what this NH Hill coefficient is representing is the degree of cooperativity among binding sites, which is always slightly or somewhat less than the number of actual binding sites. So you should keep that in mind. NH will not be 4 for hemoglobin. It will be something less than 4. Now we can look at an actual Hill plot and evaluate what happens with hemoglobin in terms of its NH value in a certain range of oxygen concentration. So we know hemoglobin has positive cooperativity, and by definition, NH must be greater than 1. But we also have just stated that NH cannot be as high as 4 because we don't really have perfect cooperativity. So we need to orient ourselves to our graph here and notice that myoglobin has an NH of 1. This is the blue line. Myoglobin is not capable of engaging in any kind of cooperativity, either positive or negative, because it only has one subunit and it has no opportunity to even behave in a cooperative manner. Hemoglobin, on the other hand, of course, does have cooperativity. And the part of the graph that we want to zero in on to understand what our NH is this part right here. Because this is where the slope has actually departed from NH equals 1. Now this is a bit artificial and a little too perfect, but there are areas of oxygen concentration where hemoglobin's really not showing cooperativity, and NH is equal to 1. But this, again, this region right here, where NH equals 3, says this is the degree of cooperativity in hemoglobin. So this is what you want to look for when you're evaluating a Hill plot. Now, if it were negative cooperativity, of course, this slope would not be positive. It would be negative. So you can try to imagine different scenarios depending on positive, negative cooperativity, and the nature or the quantity of the slope. In talking about cooperativity, I want to just give kind of a brief summary of 2 models of cooperativity. One is the Monod-Wyman-Changeux model for cooperativity, which is called the MWC or concerted model. In this concerted model, the proposition is that upon the binding of oxygen in the T state, it's an all or none transition, meaning that all subunits go from the T state to the R state upon the binding of oxygen, whether it's 1 oxygen, 2 oxygens, 3 or 4. Now this, upon first examination, might sound like perfect cooperativity. If you're going from all T to all R, why would this not be an example of perfect cooperativity? Well, the reason for that is equilibrium. Notice, if you evaluate these arrows, the R state is more strongly favored, courtesy of equilibrium considerations, when we have more oxygen bound, versus 1 oxygen bound, which only mildly favors the R state. So this is the concerted model, and you should indeed note the shift in equilibrium as more O2 binds. The model that may make more intuitive sense to you is something called the Coachland model for cooperative binding. And this means that upon the binding of oxygen, yes, we will provoke a transition from the T state to the R state, but it's not all or nothing. We may just provoke a transition from the T state to the R state in 1 additional site or 2 additional sites. There are many variations apart from the one you see here of the potential transitions, but the main thing to know is it's sequential, not all or nothing, and that a conformational change in one subunit has the ability to trigger a change in the next subunit. Equilibrium, again, is a consideration here. The more oxygen that binds, the more we favor an equilibrium towards the R state. Next, we want to think about how hemoglobin also is capable of transporting hydrogen ion and carbon dioxide. So these are end products of cellular respiration, a process that we're going to be talking about later in this course. But in fact, hydrogen ion and carbon dioxide are produced by cellular respiration. There is an enzyme that catalyzes the hydration of CO2 to bicarbonate. So if CO2, one of these end products, combines with water, we get even more hydrogen ion and the bicarbonate. Hemoglobin transports about 40% of the hydrogen ion and 50% to 20% of the carbon dioxide that is formed in the tissues to the lungs and the kidneys. If they get to the lungs and the kidneys, they can then be disposed of. Another thing to take note of is the binding of hydrogen ion and carbon dioxide is inversely related to the binding of O2. We're going to examine that in more detail on the next slide. Cellular conditions impact whether it's going to be H plus and CO2 that bind or O2 that binds. So the Bohr effect describes the effect of pH and CO2 on the binding and release of oxygen by hemoglobin. So we just said, or I just said a moment ago, that hydrogen ion concentration and CO2 are inversely related to the binding of oxygen. Let's examine that in the context of this equation right here. If hydrogen ion concentration is high, this is going to shift the equilibrium of this equation to the left. And it's going to mean that we have oxygen being released from hemoglobin and hydrogen ion binding to hemoglobin. On the other hand, if oxygen concentration is high, this will shift the equilibrium of this equation to the right, meaning more oxygen will be bound to hemoglobin and hydrogen ion will be released. So that's the basics of that inverse relationship between hydrogen ion concentration and oxygen concentration. Taking that to the next step, if we lower pH, by definition, this means increased hydrogen ion concentration and lower binding of oxygen, because this becomes the predominant form. Now, we need to turn our attention to the graph now, because at lower pH, our fractional binding curve changes. Notice at a pH of 7.2, again, relatively high hydrogen ion concentration, this curve has shifted to the right. When this curve shifts to the right, this means it takes a higher oxygen concentration to get to the same level of binding. To illustrate this, let's just look at half saturation or half binding. And if we go across, we have 3 different points on our 3 different pH lines. At a pH of 7.2, we have to get to a PO2 of approximately 4 in order to get 50% binding. At a pH of 7.6, alternatively, we only have to get to a partial O2 pressure of, let's say, 2.6 kilopascal. So again, lowering the pH increases the hydrogen ion concentration and means that we need a higher partial pressure of oxygen to get the same amount of binding. The reverse, of course, is also true. The higher the pH, the lower the hydrogen ion concentration, and the easier it is for oxygen to bind. You should study this graph and get yourself well familiarized with the Bohr effect and how it works. Now we can turn our attention to another compound called 2,3-bisphosphoglycerate, which is the compound that you see right here. It is, as noted previously, a compound that is capable of heterotropic allosteric modulation. It actually binds at a site on hemoglobin distant from the oxygen binding site. And it's quite interesting what it does. It actually regulates the delivery of oxygen to 40% of what hemoglobin could actually transport. So, translation, BPG greatly reduces the affinity of hemoglobin for oxygen. And we're going to see in a moment how concentration levels of 2,3-BPG actually vary physiologically and the implication that has for oxygen affinity to hemoglobin. The case study that we want to familiarize ourselves with here is the effect of BPG on O2 binding to hemoglobin under 2 different scenarios, namely high altitude and sea level. Now, as you can imagine, at high altitude, we actually have less oxygen, a lower partial pressure of oxygen available in the atmosphere. And sea level, i.e. normal conditions, everything is, functioning as normal. So, BPG increases over time at high altitude. And the reason for this, the reason BPG increases at high altitude is its presence has a small effect on the binding of oxygen in the lungs, but a substantial or considerable effect on the release of O2 in the tissues. As a result, with an increase in BPG, the delivery of oxygen to the tissues is restored to the 40% that we want and normalizes our ability to function at high altitude. In order to understand this, we have to take a deep dive into this graph. So let's establish some baseline conditions here and parse this graph. BPG typically is at 5 millimolar concentration. By the way, we all have some level of BPG. It's never 0. We have a typical level of 5 millimolar at sea level, and this is the behavior of our binding graph here is represented by the blue line. The green line, on the other hand, represents an increase in BPG to 8 millimeter at high altitudes. So how does this work? Well, the first thing we want to look at is this close to 40% figure that is the desired number. And notice if we turn our attention to the blue line, i.e. sea level conditions and 5 millimolar BPG, that we have a high level of binding of oxygen in the lungs at sea level, and then the release in the tissues at sea level is here. If we follow this line, we notice the difference here is 38%. Now, if we were to shoot up to high altitude, if we go to the top of Mont Blanc or something, and our BPG levels have not had a chance to adjust, in other words, they're still at 5 millimolar, notice that we're only going to release 30% of the oxygen acquired in the lungs to our tissues. So the difference here is 38% drops down to 30%. This is bad news because we want more than 30% of the oxygen being picked up in the lungs being delivered to the tissues. What happens if we increase BPG to 8 millimolar? Notice that this is quite interesting. This is PO2 in the lungs right here, right? We pick up a certain amount of oxygen here in the lungs. We're going down to the green line now. And we release it in the tissues down here with the curve shifted to the right. This restores the release to about 37%. 37% is quite similar to 38%. So by increasing the BPG concentration, we've restored the amount of oxygen being delivered to the tissues by increasing the level of BPG. But why is that exactly? What did shifting the curve to the right do for us? Well, notice we said here, increase has small effect of binding of O2 in lungs, but considerable effect on release of O2 in tissues. So when we say not a very big effect in the lungs, we mean the difference here between BPG 5 millimolar and BPG 8 millimolar is actually pretty small. The purple line here represents the difference in binding. Slightly lower when we have BPG of 8 millimolar, but not hugely different. However, if we do the same evaluation for the tissues, notice the difference gets much bigger. So minimal effect on binding in the lungs and maximal effect on release in the tissues, which is how we get back to this 37% number. So takeaways: BPG rises at high altitudes. In doing so, it shifts our fractional binding curve to the right. That restores the release of oxygen to normal levels. How does BPG fulfill its modulating function? Well, as we know, it limits the ability of hemoglobin to carry oxygen. And as such, it actually, interestingly, has a role in cooperativity through heterotropic modulation. The way it does this limiting factor is it binds to the cavity between beta subunits in the T state. So you see the BPG molecule in here, and this stabilizes the T state over and above the R state. And that's how BPG, in very simple terms, does its business. It just so happens that the cavity between the beta subunits is lined with positively charged residues. If you go back and look at the structure of BPG with its phosphates, you'll notice that it's got a lot of negative charge, so hence its ability to bind in this cavity. Okay, finally, we want to wrap things up with a brief discussion of sickle cell anemia because it's certainly closely related to the health and wealth of hemoglobin. And sickle cell is a homozygous condition. It involves a single amino acid substitution. Glutamine 6 is changed to valine 6. This produces a hydrophobic patch in the beta chains of hemoglobin, those two beta subunits. And this is bad news for hemoglobin because it leads it impairs its ability to carry oxygen. Why does that happen? Well, the deoxygenated hemoglobin, since oxygen can't bind, actually becomes insoluble. And this forms polymers of proteins that aggregate together. We have seen before that aggregation is generally bad news if we have protein aggregation. Recall we were looking at neurodegenerative diseases that arise from this kind of situation. So the hemoglobin is no longer soluble. The cells, these fibers cause the cells to sickle, and alternatively, normal hemoglobin actually is able to remain soluble upon deoxygenation. We know it has different states, right? Okay, so that's it for our lecture here, and do spend some time understanding some of the trickier aspects, things like the Hill equation, the Bohr effect, and the BPG considerations.